We've now seen, in looking at series with negative terms, if we have what we can tell is an alternating series, then a natural test to use is the alternating series test. But consider this example we have here, where the sum is from k equals 1 to infinity, and our terms are sine of k over k squared. Because sine of k is going to oscillate through both positive and negative terms, this series certainly has negative terms. But it is not alternating. And the reason for that is if you think about this sine function, you can have sine of two integer values in a row where the SIGN sign of those terms is the same. So I could have positive, positive, followed by a negative, maybe a slew of positives, and so on. So this is going to have both positive and negative terms, but we can't say that every other term, the sign of the terms changes. So if it's not alternating, we can't use the alternating series test. So even though you might see some negative terms, that doesn't mean we can automatically apply the alternating series test. So what would we do in this instance? Well, there's a theorem that we can take advantage of known as the absolute convergence theorem. And this theorem says that if the sum of the absolute value of the terms converges, then so does the sum of just the terms by themselves. One thing I want to emphasize here is the placement of those absolute values. So that's very specifically inside of the sum. So it's not that we find the sum and then take the absolute value at the end. That would be on the outside of the sum. But here, every term is made to be positive. In our example that we're looking at here, we're going to think of this as a sub k. So we want to know if this series converges. What we can say is that in this instance, if I were to take the sum of the absolute value of this series, my hope is that I can show that this converges, and then I can say that the absolute convergence theorem tells us that the original one does. So let's think about what we gain by taking the absolute value. Well, first of all, the key thing here is that this series that we're looking at now has all positive terms. So the advantage there is this opens up the possibility of using some of our tests that required that we have all positive terms, which we couldn't use on the original series. In particular, we can try to use the comparison test here. And what I'm going to keep in mind is that we know that sine of k is between -1 and 1. If I take the absolute value of sine of k, consequently that lies between 0 and 1. So with that in mind, we can bound this sum above by the one with a just 1 in the numerator based off of our pink inequality. And we know that this resulting series converges. It's a p series with p, which here is 2, strictly greater than 1. So what I'm allowed to say is that, notice that I'm not jumping straight to the original series, but what I can say at this point is the sum of the absolute value of our terms, that converges, and my justification is that's by the comparison test. So these last two lines here are a complete justification that the sum of the absolute value of the terms converges. However, that allows me then to say that the original series converges, and this only requires one extra step of referencing that theorem. So I can say that the sum from 1 to infinity of sine of k over k squared also converges, and this is by the absolute convergence theorem. So let's look back at this real fast. A common mistake is for somebody to simply say that the original series converges by the comparison test. The problem there is that you can't use comparison test unless both series that you're using in your comparison there have all positive terms. You could imagine we could bound a sum above, but it could still diverge to negative infinity. So we have this restriction that we really need the terms to be positive. So in order to use the comparison test, we must also use the absolute convergence theorem. So these need to go together here. But what we've written is a complete justification that this series converges. I do want to emphasize, as is often the case with things we've been looking at with series, we have to be very careful with the direction of our implication. So the theorem says that if the sum of the absolute value of the terms converges, then the sum of just the terms themselves converge. If I swap out the word converges for diverges, that tells me absolutely nothing about the original series. So we don't want to get into the habit of always assuming that the two series behave the same. What we're very specifically saying here is that if the one with all positive terms converges, then the one with potentially positive and negative terms must also converge. And that's the only direction we can use. So just as a kind of reminder or a counterexample to keep in mind, let's look back at the alternating harmonic series. I believe we've seen this with exponent k minus 1. The only difference here is that which terms are positive and which are negative. So you can see the alternating harmonic series either like this or with, say, negative 1 to the k minus 1. But again, for our purposes, I'm going to think of this as our a sub k. And if I were to take the absolute value of those terms, we would get the harmonic series. And I'm not going to write out the full justification here, but we know that the harmonic series diverges. But the alternating harmonic series, if you were going to apply the alternating series test to this, you would see that this converges. So we see here that the two don't behave the same in this potential instance where the original one diverges. And again, it's of course possible that you have a scenario where they do both diverge. But what we see here is that's not an obvious conclusion. So you just want to be very careful about that. Given this notion of the absolute convergence theorem, this leads us to a point at which we can further classify what convergence means. So, of course, we still have our definition of convergence, but we can make categories within. So now when I'm talking about convergence, we're going to break that up into one of two types. So if a series converges absolutely, then that means that the sum of the absolute value of the terms converge. Now, one thing I have in parentheses here is that if the sum of the absolute value of the terms converges, the previous theorem automatically tells us that the sum of just a sub k converges. So what you can think about here is that absolute convergence means both converge, the sum of just a sub k as well as the sum of absolute value of a sub k. Then we have another type. We're going to say that a series converges conditionally if the series converges, but the sum of the absolute value of the terms diverges. So the connection here for both of these, and hence the word converges, is that the sum of a sub k converges. So we would establish that, we know it converges, and then if we had to further classify, we would then look at the sum of the absolute value of the terms and try to decide if that converges. We call that absolute convergence, and if it diverges, we call that conditional convergence. So just to make sure this is clear, it's not that this is contradicting our previous idea of convergence. Instead, think about if I had a picture here of the collection of all possible series. We've seen that some converge and some diverge. And what we're doing here is we're not touching anything on diverge. There's still only one kind of diverges. We're not interested in further classifying that. But now what we're doing is we're going to split up this side and say that on top of that, we could either have absolute convergence or conditional convergence. So these are just kind of subsets of our notion of convergence. And importantly, if I'm thinking about that we want to know if a series converges, both of these new categories still satisfy that the series converges, whereas we still have the other category, diverges. We just haven't split that up into anything. Okay, so one thing that would be a reasonable thing to wonder is, why are we bringing this up now after we've looked at so many different tests? And the reason is that when we were talking only about series with positive terms, then there is no notion of conditional convergence. A series that has all positive terms will either diverge or it will converge absolutely. And the reason is that if you take the sum of the absolute value of such terms, you just get back the same exact thing if every term is positive. So before we encountered negative terms, this wasn't a very interesting question because conditional convergence was impossible. But now that we consider series with negative terms, we can start to open up to that idea that we have two kinds of convergence. So to make this idea hopefully a little bit more concrete, let's look at some examples where we can quickly categorize them. So if I encountered this series here, the sum from 1 to infinity of -1 to the k over k squared, the first thing I could do is check to see if this series converges. And again, for notation, I'm thinking of this here. To check to see if it converges, I would note that it's alternating and try to apply the alternating series test. So I can say that the limit as k approaches infinity of the absolute value of these terms, 1 over k squared, is 0. And I can also say that the size of the terms is decreasing. So both of these hold. So we know that the original series here converges by the alternating series test. And then if we were asked, is it conditional or absolute, we'd have to then check a related series. So right now, I've kind of ruled out the possibility of falling on the red side. So if I then want to check what kind of convergence, so here the question is conditional or absolute, then we look at the sum of the absolute value of our terms. And that's the sum of 1 over k squared. That is a p-series, right? We know that that converges. So altogether, now I've fully justified my conclusion about both the sum of a sub k and the sum of the absolute value of a sub k. And I see that they both converge. So I would be able to claim that the original series, the one that had positive and negative terms, converges absolutely. One thing I'll emphasize here is I don't need to follow this up by stating any test, because along the way I already justified my individual conclusions. So here I'm just really wrapping it up to say, what is it that we've learned from this? In class, I'm going to go through several examples in full detail of kind of how do I decide if a series converges absolutely, conditionally, or diverges. And I think part of the process is that there's more than one pathway to get there. So looking at this example, I just want to pause and say that an alternative way to answer this question is to start. So you could start here. So what I mean by that is, suppose I didn't apply the alternating series test. I just jumped right into this step of looking at whether or not the sum of the absolute value converges. If I show, like we did here, that the sum of the absolute value converges, then you automatically know that the original one converges by the absolute convergence theorem, which you could reference, and then you wouldn't have to use the alternating series test. So this would also be a suitable way. So notice that where I start, do I look at the original sum? Do I choose to look at the sum of the absolute value of the terms? There's lots of flexibility there, and just kind of thinking about the different ways you might go about it can help you think about how you might approach other examples. As is the case with most things we've encountered, the more practice you get, the easier that's going to be. So here's a classic example we just gone through of converging absolutely. If I change that slightly, so instead of a k squared, I go to k in the denominator. Let's again think about the same approach. If I were to go through this process and check if this sum converges, I might first observe that it's alternating, and I can apply the alternating series test. Here we would show that 1 over k approaches 0. And likewise, that 1 over k plus 1 is always smaller than 1 over k. So together, this tells us that our original sum, let's write what it is, converges by the alternating series test. So again, we would encounter the question, is it conditional or absolute convergence? Which would require me then to look at the sum of the absolute, the absolute value of the terms, which becomes just the harmonic series. This series diverges. You could say it's harmonic, or it's a p series that is into the category of less than less than or equal to 1. So what we have here is, again, I fully justified what each of these series does, and together we can now conclude that the original sum, while we found that it converges, we've now seen that it converges conditionally. Now, to pause and think about what I said before, you could also start with the sum of the absolute value of the terms like we did here. However, because that diverges, that doesn't give us any information about the sum of a sub k. So we would have to go back and check the sum of a sub k anyways. So in order to kind of get this conditional convergence, there's not really any shortcut. We really do need to look at each series in turn. And again, if that's confusing, I hope that when I go through some more detailed examples and talk about the potential pathways, that will clear that up.